Okay, so equivalent vectors, that's the first one we're going to look at here. So with an equivalent vector, it has this when you have two vectors that are the same. Now, what do we mean by the same? So the same means it has the same direction, and it would mean it has the same magnitude or size. Okay, so if you have two vectors, there's one. If you have something that is in the same direction but the same size, they would be equivalent. Okay, they can't be a scalar multiple of each other. So let's just say you have 2i plus 5j. It'd have to be 2, 5. They'd be equivalent vectors. Okay, so the next thing we're going to look at now is parallel. So what are parallel vectors? So basically, the difference between a parallel vector and an equivalent vector is that when you have parallel vectors, they will be scalar multiples of each other. Now, they can basically be in the same direction or in the opposite direction. But they're kind of going to be sloping at the same angle, as you would think that parallel lines would be. See, they're sloping. They can be different sizes and they can be in opposite directions. Because even if they're in opposite directions, if they're in the same, like sloping at the same angle, even like, say for this one, it's the obtuse angle, then they would still be parallel to each other. So how do you test if something's a scalar multiple of each other? So for example, say you have 2, 4 and you have 8, 16. So if you factorise out the 2 out of this first one, it comes out of the 2, so that's 1, and out of the 4, which is 2. If you factorise out 8 out of this one, you get 1, 2. So that basically, you can look at that, you basically have the same base angle. Same base vector. So what that means is that's the x component and see that's the y, isn't it? So it means for every one you go across x, you're going to go up 2y. And that's the direction you'd be travelling. And you can see even if you went across 2, then you went up 4, it would still be in the same direction. It would just be a different length, so to be a different size. And this one here, the same. You go across 1, up 2. But if it was times 8, if it was, you had 8, you go across 8 and you go up 16. It's still in exactly the same ratio. And if you look at the gradient, which is the rise over the run, which is y on x's, will always be 2. So in order to show that two vectors are parallel, then basically all that you need to do first of all is you just factorise them and you take out the scalar. And if the resulting vector inside, like the resulting vector that is inside the brackets is the same, so it has the same x and the same y. So if it was k times xy, then the two vectors will be parallel. So further on that, like if you had minus 2i plus 6j, and then you had 4i minus 12. Oh, you don't need the j there, sorry, my mistake. So 4 and minus 12, are they parallel? That's the question. Okay, so let's have a look at this. So you got this one and this one. So if you take out the common component here, this first one here, minus 2i minus 6j plus 6j would be minus 2i minus 3j. Okay, and if you took out the 4 out of the other one, that would be 1 and minus 3, or 4i minus 3j. So what I want you to notice is they have the same base vector. The only difference is that this minus 2 just means it is in the opposite direction, and this 4 here is a positive, so it means it's in the positive direction. So like if you've got 1 minus 3, that means you go across 1 in the positive direction and down 3. And that's basically what your vector would look like. The difference between these two vectors is this is 4 times as big, and it's going in this direction here, and the other one's going in the opposite direction. So it'll be going, the arrow going that way, but they'd still be parallel. So this one here is 4 times the size, and this one here is 2 times the size. So the scalar, all that the scalar does is just make it bigger sizes. And the negative just makes it go the other way, but they'll still be parallel. So when you're writing out this proof, you take that out and you just go, therefore, the two vectors are scalar multiples of each other. Therefore parallel. Okay, so the next thing on our list is to look at the unit vectors. So look at unit vector. So a unit vector is actually quite a powerful tool. A unit vector we define as a hat, and that will be equal to a, and then all you've got to do is divide by the modulus of a. Now, when you're actually doing that, what you're doing is you're taking vector A and you're shrinking its modulus, and you're making the modulus equal 1. This is quite a powerful tool, because once you've got a unit vector, if you multiply a unit vector by a scalar, so say this, k, then the new magnitude will just be k. So we're just going to look at a couple of things using that rule. So first of all, I want you to find the unit vector of these. So 2 on 3, 4i minus 5j, and minus 2 minus 4. Okay, so in order to find the unit vector, you need to get the magnitude of the vector. So the magnitude of 2, 3 is the square root of 2 squared plus 3 squared, which equals root 4 and 9, which is 13. So that just means it'll be 1 on root 13, 2, 3. Okay, you could write that as 2 on root 13 if you wanted to, and put the scalar in, and 3 on root 13. Okay. All right, so if we look at this one here, the modulus of this one, well, the magnitude of this one, with the square root of 16 and 25, which is the square root of 41. So it's 1 on root 41, and then it's 4 minus 5. Okay, or you could write it as 1 on root 41, 4i minus 5j. Okay, and this one here, so the magnitude would be the square root of minus 2 squared plus minus 4 squared, and then it's times minus 2 minus 4. So it's 1 over root 4 plus 16 minus 2 minus 4, so that's root 20. Root 20 is equal to 2 root 5, so it's 2 root 5 minus 2 minus 4. And finally, the last concept we just want to look at is called the dot product. Okay, so in order to get the dot product, and the dot product seems pretty useless until you see what its power is. So say we have that's x1, y1, j, and v equals x2, y2, j. So if you did u dot v, that's the vector, the dot product. It's also called a scalar product because the result is a scalar. So it'll be x1 times x2 plus y1 times y2. Now that is actually on your formula sheet. So just using it, so if u is equal to minus 2 minus 3 and v is equal to 4 minus 3, then u dot v will equal minus 2 times 4 plus minus 3 times minus 3. So it's minus 8 plus 9, which equals 1. So you basically, all you're doing is you're multiplying the x's and then you add it together and you multiply the y's. So that's the first one. So let's go u equals minus 3i plus 5j and v equals minus 2i minus 4j. So if you wanted to find u dot v, that would be minus 3i minus 5j. Sorry, let's take that back. We want the dot product. So let's multiply the x's. So that's minus 3 times minus 2. Multiply the y's, so that's 5 times minus 4, and add them together. So it's x1, which is minus 3, times x2, which is minus 2, plus 5 times minus 4, plus 6 minus 20, which equals minus 14. And that's the vector dot product.